Hi, this is Chuck Benedict, mentor for Team 997 Spartan Robotics in Corvallis, Oregon. Back with another video in my series on creating a device driver for a RGB color sensor. In this video, I am going to go through the color sensor datasheet and using a device called a bus pirate, I am going to interpret the datasheet to trying to actively interact with the RGB color sensor without having to write any code. And so the objective for the video is to walk you through, for those of you that haven't done this before, to walk you through reading a data sheet, because when you look at these things, they might appear to be very intimidating at first, but I'll try to break it down so that you can look at the pieces in little chunks, and we'll make some sense of them. And then we will hook up the device to the bus pirate, and we will go through a terminal emulator program and send commands to the bus pirate to see if we can exercise the device using the knowledge that we've gained from the datasheet. So grab yourself a cup of coffee and get ready, because this video is probably going to be lengthy, but I think this is a tremendously important skill to learn if you haven't done it before. And I think this would be useful for both folks in the electrical groups as well as those in programming, because this sort of straddles the fence between, understanding electrically how something works and the data that you send to something to make it work versus on the programming side, when you write code, you're essentially going to be doing the things that we're going to be doing through the terminal emulator. So if you know how to do that ahead of time, it makes writing the code a lot easier. So here we go. First things first, the data sheet. So we are dealing with a TCS34725 RGB color sensor. The one that I got is actually this one, purchased from Adafruit. And the data sheet off of Adafruit's site links you to this data sheet. Texas Advanced Optoelectronic Solutions is the manufacturer. And so the first thing that I always look for on the data sheet, because the first thing we want to do is actually electrically connect the thing up to our bus pirate device so that we can drive it. And so we want to make sure of is this thing electrically compatible with the bus pirate? The bus pirate has two voltages that it will output to a device. And if I go look on the bus pirate data sheet, it'll tell you, and in fact, the cabling on the bus pirate shows that I've got a ground, and then I've got a plus 3.3 and a plus 5 volts. So I know I've got two source voltages that I can connect stuff to on the bus pirate. So the question is, on the color sensor, what kind of device is this? Is this 3 or 5 volt? So the first thing I always do is I scroll down to the electrical characteristics of the device, and I look at the absolute maximum ratings. And so you can see that the supply voltage here is 3.8 volts. So I know that this is a 3.3 volt device. Now, notice that there are different options available for this device. There is an option where the I2C bus is at VDD, which is at the source voltage. And there's also an option where the I2C bus is at the 1.8 volt voltage. And that's for microprocessors or processors that whose voltage is driven at 1.8 volts as opposed to 3.3, which is more common these days because microcontrollers are running at very low voltages to save power. In this particular case, I know that the bus pirate drives its pins at 3.3 volts because, again, I've read the data sheet on the bus pirate, and I know for a fact that I have the TCS34725 because that's the number that's on it. So I know that the I2C bus is driven at VDD, which is 3.3 volts. So what that tells me then, so let's go back and look at electrically how to hook this up. If we look at the bus pirate here, so I know that ground and 3.3 volts needs to go to the color sensor. So if we flip over to the color sensor, we can see that VN, that's where my 3.3 volt connection from the bus pirate is going to go, and here's ground. That's where the ground connection is going to go. Now I2C has two signaling wires associated with it. One called SDA, which is this pin right here. That's the data line, and one called SCL. That's the clock. It stands for clock line, signal clock and signal data. If I flip over to the bus pirate, what you see is this little table here, and we are going to be operating the bus pirate in I2C mode. So what that means is the SDA line on the color sensor needs to be hooked up to MOSI on the bus pirate. And you can see MOSI is this little orange pin right here. So SDA on the color sensor to MOSI on the bus pirate, and SCL on the color sensor goes to the clock pin on the bus pirate. So off camera, I have this already connected. I'm not going to show you because I don't want it to come disconnected, but trust me, that's how I have mine hooked up and it works fine. Okay, so now that that's taken care of electrically, there's a whole lot of other electrical characteristics that are in this thing. Interesting, but not particularly useful. We're going to blow past all of that. Actually, we're going to go back up to the top and read this little description, because this little block diagram is useful to kind of understand what's going on in the black box. And just by looking at this thing, I can kind of tell, okay, we've got some sensors here, and we've got 4 of them, and each one of them are going to be sensing clear, red, green, and blue light with a filter here. And we have ADC, these analog to digital converters that are going to be converting most likely current, probably current flowing in these sensors to a digital value. And this little block signifies to me that there's registers that these values are going to get shoved into. Also, here it looks like maybe there's some interrupt capability on the chip. We're not going to talk about that, but there's some limits that probably control the firing of the interrupts. I can kind of discern all that just by looking at this block diagram, but let's read a little bit of the text because I think that's useful at the intro here. So it says the digital light converter has 4 analog to digital converters that integrate the photodiode current, data registers, a state machine, and an I2C interface. The diode array is composed of a red filter, green filter, blue filtered, and clear photodiodes. In addition, the photodiodes are coated with an IR filter. The 4 integrating ADCs simultaneously convert the amplified photodiode currents to a 16-bit digital value. So this is a pretty important statement here, because this is saying that the detection of the light from each one of the 4 sensors occurs simultaneously and gets converted into a 16-bit value. So 2 bytes, 16-bit value for each one of the light sensors. It says on completion of a conversion cycle, the results are transferred to data registers, which are double buffered to ensure the integrity of the data. And what that means is that the values are sort of held in a buffer such that when the cycle begins again, if you happen to be in the middle of reading one of the 2 bytes of the value, the second byte won't get overwritten by the detection that's going on subsequently. Next, it says communication of the TSC34725 data is accomplished over a fast up to 400 kilohertz 2-wire I2C serial bus. So this also tells me that the I2C bus is running at 400 kilohertz, which is important because you need to know what rate to drive the bus pirate at. Some other stuff here, it's useful, but we're, in the interest of time, not going to read it. Okay, so we've learned some good stuff already. We're going to continue reading here because this state machine, for sensors that run in a continuous loop for you, where you don't have to drive the running of them, these are called, I'm going to call this a free running sensor. It usually has what's called a state transition diagram in the datasheet. And this state transition diagram will tell you all of the various states that the sensor is going to run in and give you either register values or bit values that control and tell you what state it's running in. And the reason this is important is because you need to know what bits or registers to set in order to get the device running the way you expect it to run. So it says an internal state machine provides system control of the RGBC and power management features of the device. At power up, an internal power on reset initializes the device and puts it in a low power sleep state. So this already tells me that when you start the device up, it starts up in a low power sleep state, which means it's not going to be running or doing anything, which then means we're going to have to send some information to it to get it to start up and start sensing color values. So when a start condition is detected on the I2C bus, the device transitions to the idle state. So here we see it's in a sleep state. But when we start it up, then it transitions to this idle state. And the way you start it up is where it checks the enable register, hex 00, and in particular, it's going to be checking the PON bit, which stands for power on. If power on is disabled, the device will return to sleep state to save power. So that means it can flip back into sleep state if you set the power on bit back to 0. Then it says otherwise the device will remain in an idle state until the RGBC function is enabled. So there must be some other bit or register called AEN that we have to flip to get it out of this idle state into these other states. So once enabled, the device will execute the wait and RGBC states in sequence as indicated in Figure 5. Upon completion and return to idle, the device will automatically begin a new wait RGBC cycle as long as PON and AEN remain enabled. So this one little paragraph tells you a whole lot about how it is that this sensor is going to be operating and what you're probably going to have to do to be able to turn it on and get it to start sensing color values. All right. So let's, so the next thing that I usually do, so we kind of already have an idea of what it is that we have to do to the device to get it to actually sense. But the first thing that I want to do with the device is confirm through my terminal emulator program. And let's talk a little bit about that for a second. I have a terminal emulator program called RealTerm. It's open source. I'll have the link to it in the comments on the video. You can download it, install it, very simple to install. And what this does is communicates through a serial port, a virtual serial port, to the bus pirate, because the bus pirate outputs a user interface to you in old school command line format, which looks really ugly, but it's pretty powerful because it allows you to very easily send commands to the bus pirate without a whole lot of eye candy of graphical user interface. So I have the bus pirate plugged into my workstation here already, and I know that the baud rate, the default baud rate of the bus pirate is 115200 because that's what the datasheet says on the bus pirate. And so I go through and I pick all the serial ports, and I happen to find that on my workstation, port 4 VCP3 is the one that is connected to the bus pirate. And when I click this change button, and on RealTerm you have to click change to open the serial port, when I hit enter, I get syntax error type question mark for help and high Z as the command prompt. And that's how I know that the bus pirate has power and I'm talking to the correct serial port on my workstation. I can also type question mark and I get a menu of commands, which is, you know, pretty dense to read, but pretty self-explanatory about what it is that you can do. Also, the bus pirate is a product of a company called Dangerous Prototypes. They've been around for a long time. This is what their page looks like for the bus pirate, and all of the menu options that we saw over here on the terminal emulator, they're all documented here on their website in much grander detail. We're not going to read through these directly. I've already got the commands known that we're going to exercise through, and I'm just going to talk through them without having to go back to the documentation. But again, in the comments, you can get the link to this page and read how to operate the Bus Pirate in some more detail. So first thing that I want to do, my Bus Pirate is actually pretty old. I bought this thing many years ago, and the firmware on it's pretty old. So the first thing that I want to do is show you what version of the Bus Pirate I've got. Let me clear this screen here, clear, and I'm going to hit I. I is the command to give you information about the Bus Pirate that you've got. I'm running firmware version 3.0. I think they're up to version 6 or 7 or something. For this video, it's not particularly important because the commands I'm going to use have been around for a long time, but be aware that the documentation that you're reading and the version of the firmware that you may get when you buy the Bus Pirate may differ. So commands that are documented may not actually be on your Bus Pirate unless you're operating the same version. Just be aware. Okay, so we have the Bus Pirate connected, terminal emulators connected to it. That's all great, and I know what version I'm using. So first thing that I typically do is most devices have a way to identify them to code or to a user or whatever, kind of like a sanity check for you to make a determination that the device that you think you're talking to is actually the device that you're talking to. And so down in the depths of the datasheet, the first thing that I usually do to confirm that I'm talking to the device that I think I'm talking to is I go down into the depths of the datasheet and I look for something called identify. So I'm just going to do a search on identify. I can spell it correctly. And lo and behold, it appears well, I say that, and it, oh yeah, it does. It appears several places in the document. Here we go. Part number identification. So this winds up being on page 18 of the document. You can read the whole thing if you want, but we're looking for part number identification. Most components have a way to identify them. In this case, the ID register, and let's digress for a second. Devices like this have things called registers, and think of a register as nothing more than a variable that stores some information. Instead of in Java, where you can name your variables nice names, devices like these, they don't have names, they have numbers to identify the registers. And the numbers are usually identified in hex. That's what 0x means. So this is hexadecimal 12 that we're using to identify this register, this ID register. So when we go to the Bus Pirate, we're going to be identifying register 12, and we're going to be asking to get the contents of register 12 out. And when we do that, you can see right here, we should be getting back hex value 0x44, and that is for the TCS part 34, 721, and 725. You'll remember when we looked up at the top, there were 4 variants of this product, and if you have the other variant, you're going to get a different identifying code. Okay, so let's see if we can formulate an I2C message using the Bus Pirate to read this identification register, register 12, and see if the Bus Pirate will return back the contents of the register and if the contents is 44. How the heck do you do that? So back up at the top, not at the top, but sort of midways in the document here, they have a discussion of the I2C protocol. This discussion here gives you what you need to know on how to send a message to the device And what we need to do is figure out how to translate this from this format to what the bus pirate understands. So what we want to do is that we want to send the register. We want to tell the device, I want you to read the contents of register 12, and I want you to read 1 byte at that register and send it back to me. And the way that you do that, if you look here at this third diagram, we want to send S. What the heck is S? That's a start bit or start condition, documented up here. We want to send the slave address, and that's 7 bits plus another bit with W. What the heck is that? We'll get to that in a second. The device is going to send you back an A, or an acknowledgement that it got this byte. Fine. Then we're going to send a command code. What the heck's a command code? Well, the command code is actually the register that you're trying to read, plus a little bit of extra. We'll go to look at what the command code actually is here in a second. And when you send that, you get back from the device another acknowledgement. Then you send another start, this SR here. That's basically another repeated start condition. Then you send the slave address again, which is the device that you're talking to, with an R. And what the heck is that? That's a read. You're telling the device that you want to read. And we'll talk about how you formulate this byte here with this 1 bit of read set. You get an acknowledgement back from the device again. Then we want to read data. You'll notice with this command, you can read multiple data bytes at a time. But in this case, for the 12 register, there's only 1 byte that we're trying to read. So we only read once. Great. So how do we do all that in the bus pirate? So I just turned the bus pirate on, and I've done nothing else. So what's the first thing that we need to do? First thing that we need to do is you'll notice that the command prompt says hi Z. So we need to tell the bus pirate that we want to communicate in I2C mode, because right now it's in what's called raw mode, which is to really say that there's no mode at all. So how do you do that? Use the M command for mode. You get a nice menu here of all the modes supported, and number 4 is I2C. I'm going to pick hardware, and from the data sheet, remember the color sensor runs at 400 kilohertz, so I will go ahead and pick 2 for 400 kilohertz. Great. Now I get an I2C prompt, and if I look at the bus pirate, let's see if I can hold it up without screwing up. You got 2 LED lights on. There's a LED light labeled mode, and that light's lit, so I know that I've flipped it into a mode that's not raw mode, which is great. Okay, so next, the bus pirate's on, but the color sensor is not, because the bus pirate by default does not assert voltage to the voltage out pins unless you tell it to. So the way that we do that is with the W command. And you get power supplies on from the terminal emulator. And if I look back over, I'll hold it up again. You can see I have a light on the sensor, so I know that the sensor's got voltage, which is wonderful. Okay. Now, we want to formulate this identification message. So how do we do that? Let's go back to the data sheet. And what we want to do is we want to send a start condition. And on the bus pirate, if I do question mark, a start condition is done with an open square bracket. So there's my open square bracket. Next, we want to send the slave address. However, the slave address is in bits 7 through 1, and then in bit 0, in the final bit, we want to send a W, which translates up here to a 0. All right. How the heck do we do that? How do we figure that out? Well, one way is we can take, remember from the top of the data sheet, address 29 is the address that we're speaking to. There's up to 127 addresses that you can address on an I2C bus, because each device typically has a read address and a write address. So there's 1 byte for a total of 255 options, but the last bit is dedicated to whether you're reading or writing. So that's why you have 127 potential addresses. So we could bit shift address 29 with a calculator, but I have a cheat and an interesting feature on the Bus Pirate. So back here, I am going to put a start and stop here, and instead I'm going to issue a macro command, in this case paren0 paren, which lists for me out all of the macro functions on the Bus Pirate. You'll notice number 1 says 7-bit address search. If I pick 1, I get the Bus Pirate to scan the I2C bus to enumerate all of the addresses that it sees a response. It'll send a request out to each one of them, and any one that it gets a response back for, it'll report. Notice that 29 for writing is hex 52, and 29 for reading is hex 53. So now I know what the slave address needs to be when I formulate the address to the Bus Pirate. So start, and my slave address, back to the data sheet, my slave address for writing, or my slave address is for writing at the beginning here. So I know that writing is hex 52, so 0x52. Next, this is the command code to send, which is the 12 hex 12 register to read the identification number out of. However, it's not quite that simple because it's a command code. What the heck is a command code? You got to go down in the data sheet in the section that covers the command register. Command register specifies the address of the target register for future read and write operations. Great, that's what we want. However, bit 7, it says select command register must write as 1 when addressing command register. So what that tells me is that bit 7 has to be flipped to 1 always when we're trying to write the register that we're either going to read from or write to. And also notice that the address field is bits 4 through 0. So hex 12 needs to go in bits 4 through 0, which that's all the way to the least significant bit. So how do we figure that out? Easiest way is the Windows 10, there's a calculator. So I know that the bit 7 always has to be flipped. So let's put a 1 in for bit 7. And remember, bit 7 is the most significant bit in an 8-bit byte. And now I want to OR this to hex 12, which is the register we're trying to read from. So I hit OR, I flip over to hex, I type in 12, and I hit equals. So I get hex 92. That is the command back on the data sheet. Back up to the protocol definition. That is the command code, the 8-bit command code that I want to send. So back over to the Bus Pirate, I type in 0x92. Great, we're making progress. Next, we want to send another start, repeat start condition. That's easy. That's just another open bracket. Next, we want to send the slave address again, but instead of the write, we want to send the read slave address. So back to the Bus Pirate. You'll remember when we enumerated the bus, we found that the read address was hex 53. So I type in 0x53. Next, we want to read 1 byte of data. How do you do that? Well, in the Bus Pirate, there is a command called R, documented, where it's on the menu. My menu must be messed up. Trust me. Oh, there it is. It's R. So we want to just read 1 byte, so it's R, and we want to finish with a stop bit, which again is defined over here as P, and P means stop condition. So on the Bus Pirate, that's a closed bracket, and if I hit enter and cross my fingers, oh, looky here, I get a read of hex 44. So I know I'm talking to the Bus Pirate, and I'm getting back, and through the Bus Pirate, it's talking I2C over to my color sensor, and the color sensor is responding back with a data value that I expect from the data sheet. So I know how to formulate the message in the Bus Pirates command language, and know how to read the datasheet to get a basic message to it, to send a register, to get something back. So far so good. I'm doing well. I'm going to stop the video now before going on to actually reading the color sensor values because it's going pretty long. It'll give you a chance to get a break. Next video, we'll cover reading color sensor values. Thanks for watching.